This video covers section 8.1, Sequences and Summation Notation. The definition of a sequence is the set of terms defined by the notation a sub n, which represents a function whose domain is the set of positive integers, meaning 1, 2, 3, 4, 5, 6, etc. So when I plug in the value of 1 for n, we get a sub 1, and this would be given as a formula to calculate that number. A sub 2 means the second term of the sequence. A sub 3 is what I get if I plug in 3, that's the third term, and so on. Each of these numbers are called terms, and the subscript will indicate the position in the list. So we're going to do an example here first, just to show how to utilize a function given that represents a sequence. Write the first four terms of the sequence. A sub n equals negative 1 to the power n plus 1 divided by 2 to the nth plus 1. So to find the first term, we're going to let n equal 1. So if I plug in a 1 for n, we would get a sub 1. We also plug in a 1 for n everywhere we see it here. So negative 1 to the power 1 plus 1, 2 to the first power plus 1, and then we simplify. Negative 1 to the second power divided by 2 to the first is 2 plus 1 is 3. So when I square negative 1, I get a positive 1, so 1/3. The second term, a sub 2, means I'm going to let n equal 2. So negative 1 to the power 2 plus 1 divided by 2 to the second plus 1. So the numerator would become negative 1 to the third. 2 squared is 4 plus 1 would make the denominator 5. When I cube negative 1, I get a negative 1. So I get negative 1 over 5. Term number 3 means let n equal 3. Negative 1 to the 3 plus 1 divided by 2 to the third plus 1 becomes negative 1 to the fourth power. 2 to the third is 8 plus 1, 9. Negative 1 to the fourth is a positive 1, so 1 over 9. And then our fourth term, when I plug n equals 4n, a sub 4, negative 1 to the power 4 plus 1 divided by 2 to the fourth plus 1. So we get negative 1 to the fifth on top. 2 to the fourth is 16, plus 1 would make the denominator 17. Negative 1 to the fifth power again is negative 1, so negative 1/17. Next, we have to talk about factorial notation to understand a few other things you're going to see in this section and part of what we will cover in the next section. The word factorial in math is indicated by the notation, this exclamation point following a number. So factorial notation is defined to be a number n, factorial is how you would read the exclamation point, equals, you would start with the value of n and then multiply that by one number smaller and then another number smaller all the way down until you've multiplied by a 1. So for example, if n was 5, 5 factorial would mean start with 5, then 5 minus 1 is 4, 5 minus 2 is 3, etc. So 5 times 4 times 3 times 2 times 1 and multiply together. So when I multiply those numbers together, I would get 120. So this notation is defined for positive integer values of n. There is a special case if we ever had to encounter 0 factorial. We can't back up and land at 1, right? So that would not apply with this formula, but we have a special case that we define the value for 0 factorial to equal 1. That's necessary for certain things in mathematics to work correctly. So that is just a definition. So we'll do another sequence example. This time our formula happens to involve the factorial notation. A sub n equals the quantity n plus 1 factorial divided by n squared. And we need to write the first four terms. So if I let n equal 1, a sub 1 would give me 1 plus 1 factorial over 1 squared. So that would make the numerator 2 factorial. 1 squared on the bottom is still 1. So 2 factorial would just mean 2 times 1 over 1, which is 2. A sub 2 I plug n equals 2 into my formula, 2 plus 1 factorial over 2 squared. That means 3 factorial over 4. 3 factorial would be 3 times 2 times 1, which would be 6. So 6 over 4 would reduce to 3 over 2. The third term, 3 plus 1 factorial divided by 3 squared, becomes 4 factorial over 9. So 4 times 3 times 2 times 1 over 9. That's 24 divided by 9, and then this reduces by a factor of 3, giving me 8/3. And then finally, a sub 4, 4 plus 1 factorial divided by 4 squared is 5 factorial divided by 16. So 5 times 4 times 3 times 2 times 1 over 16, 120 over 16, which reduces to 15 over 2. I do not believe in my math lab they will allow decimals for these values if they come out not to an integer, so make sure you are able to keep them in fraction form and that fraction is simplified. So there's a couple more problems that might involve factorials. These are not sequences, these are just expressions that involve the factorial notation. 16 factorial divided by 2 factorial, 14 factorial. So here, this number is fairly large, so I could write all those numbers out, but that would be kind of time consuming. Since I'm dividing by factors that contain smaller values, we can simplify in a way that we don't have to write everything out. So we'll start with the larger number, which is in the numerator, and start writing out the factorial definition. 16 times 15 times 14, and I could keep going here, 14, 13, 12, etc. But I'm going to stop at 14 and just follow it with my factorial to mean it keeps going, because I would have those same numbers listed on the bottom if I were writing out 14 factorial. So once I hit the 14 factorial, I stop, and this 14 factorial on the bottom would not need to be written out because all those would be the same as all of these. So those would cancel. This other number here I would have to write out. 2 factorial means 2 times 1. So 16 times 15 over 2. And then you could even here cancel 2 into 16 and get 8, and then 8 times 15 is 120. Or you can multiply 16 and 15 and divide by 2. This one is similar, only here our answer will be in terms of n. So the numerator is larger, so we will start writing it out using our definition. So we start with the value n plus 2, multiply it by one number smaller, which would be n plus 1, multiply them again by one number smaller, which would be n. And I can stop here and attach the factorial because the rest of this list would be exactly what the bottom list would be. So all the rest of these numbers, n factorial, would cancel with n factorial on the bottom. And here I'm just left with the numerator, n plus 2 times n plus 1. Or if you multiply that out, n squared plus 3n plus 2. The second part of section 8.1 covers what we call summation notation. And this is just a way of shortcutting the way we write a sum of numbers using symbols. So the sum of the first n terms of a sequence is represented by what we call summation notation, or sometimes that's also referred to as sigma notation, because this symbol we use is the Greek letter for sigma. So this sigma symbol, it kind of looks like an E sort of, but it's the Greek letter referred to as sigma, stands for summation in math. At the bottom we see I equals 1, and then on the top we have an n. So this I is just the variable involved in your formula. The number we start with on the bottom is the value that we're going to begin with when we start substituting numbers, and then the value on top is the number we're going to stop with. And then you'll see a formula involving this variable, a sub I. So we start by plugging in the number on the bottom. So we would get a sub 1. Then we would move on from there. So after I plug in a 1, then I plug in a 2. But the sigma means as I plug in the next number, I'm going to add together. So add a sub 2, then I plug in a 3. So we add a sub 3 plus, and we keep adding until we get to the number that's on top, and that gets plugged in. That's a sub n. That's the ending. And then we just add these together. So a sequence means you're just listing numbers in a list. When it's preceded by the sigma, it means you're going to write the numbers of the list out, but then you're going to add them together to get one result. So the I is referred to as the index. It does not have to be the letter I. It can be any letter of the alphabet as long as this letter here matches the letter in the formula. 1 right here is called the lower limit. That's the starting value of I. It doesn't have to start at 1. It can start at any number. So whatever number is right here is the lower limit, and that's what we begin with when we start plugging numbers in. And n, whatever number is sitting up here on top, is called the upper limit. That's the ending value of I. So let's look at a few examples of how this works. The sum from I equals 1 to 5 of the expression k times k minus 2. This should say in either I times I minus 2, or this letter should be a k. That's my fault, I wrote that wrong. So this index should be the letter k, because that's the letter here, or this letter should be an I. So that's a mistake on my part. So let's assume that those were the same letter. So we would start by plugging in the 1. So 1 times 1 minus 2 plus, then I plug in a 2. So 2 times 2 minus 2 plus, then I plug in a 3. 3 times 3 minus 2 plus 4 times 4 minus 2, and then finally 5 times 5 minus 2. And I stop when I get to 5 because that's the top. And then I just clean this up. So 1 minus 2 is negative 1. So 1 times negative 1 is negative 1. This would be 2 times 0, or 0. 3 times 1, which is 3. 4 times 2, which is 8. And 5 times 3, which is 15. And then when we add these all together, we get 25. So let's do another example here. So here we have the sum from I equals 3 to 5 of the expression 2 to the power of I. So this time we just start with the index value of 3. So we start by plugging in a 3, 2 to the power of 3, plus, then we move on to 4, 2 to the 4th, plus 2 to the 5th, and since 5 again is on top, we're going to stop. And then we will simplify. 2 to the 3rd is 8, 2 to the 4th, 16, 2 to the 5th, 32, and 8 plus 16 plus 32 is 56. So that is the end of section 8.1.